Welcome to 1.3a, functions and their graph. We're going to do a little bit more work on domain and range of a function. So it asks to use the graph to find the domain of the function values -1, 2, and the range of f. So let's start with a. Let's look at our domain of our function. So remember, domain is all of the x values. And as we see here, there's an open circle there at 4, 0, and there's a closed dot at -1, 5. That closed dot tells us that we are actually equaling at -1 for x, and we are not equaling at 4. But we are going from -1 to 4. So closed bracket for -1 all the way up to 4, open bracket, because there's not an actual dot there, so it's not actually equaling the value at 4. Part B, the function values at f of -1, f of 2. So f of -1, well, let's look. Where are we at? For x is -1, we're at -5. This just means if x is -1, what's y? And f of 2, where are we at? Y is 4. And then for part C, the function, or the range of f. So from y to y, what's our lowest y value? -5, all the way up to, what's our highest value? 4. Are these points included? Are they solid points? Yes, they both are. So these would be closed brackets there for us. Okay, moving on to the next one. Find the domain and range of the function square root of x minus 4. This one falls into our domain restrictions that we talked about yesterday. If we have something under the radical and it's a even index there, we know that whatever's under the radical has to be greater than 0. So we can solve this. We know x has to be greater than or equal to 4, because it can equal 0. We can have the square root of 0. 0 times 0 is 0. And so we would have our domain there. Our domain is all of the real numbers such that x is greater than or equal to 4. We could also say from 4 to infinity, everything greater than or equal to 4. So now if we're looking at our range here, because it also said to find the range, we know that we could pull up a graph and see what this looks like, because we can do a graphical solution as well. So if we're going second square root of x minus 4 and we graph it, we can see that x has to be greater than or equal to 4. And then for all of our square root functions, it's going to be having to be for range y is greater than or equal to 0 unless it's shifted around, or 0 to infinity. Okay, great. Vertical line test. So vertical line test is a test that we can use to see if y represents as a function of x. Is it a function? Look, we have 2 points here where x is being shared. We have x and then there's 2 different y's there. So this would be not a function. We can draw a vertical line, and if it crosses at 2 or more points, then we know it's not a function. If we can draw a vertical line anywhere on our graph and it only hits 1 point, we know that that is a function. All right, next we're going to be going to looking at these ones. So these are open intervals. It's asking us to describe the open intervals for which the function is increasing, decreasing, or constant. So we know that a function is increasing, and I can just draw a little sketch over here. Decreasing means it's going downhill from left to right. It's constant if it's staying flat, and then it's increasing if it's going up. It's kind of hard to tell in this picture that I drew, but constant should be very flat, a slope of 0. So it's asking us to describe the open intervals on which this is increasing, decreasing, or constant. So right here in figure A, it might appear that there is an open interval in which this function is constant, and you can see that it implies it, but the function is actually increasing over the entire real line. It's going up, it just slows down a little bit, and it goes up. So it's actually increasing from -infinity to infinity, or all real numbers, it's increasing. It looks like it's constant, but as you can see, it's kind of curving up still. just a little bit slower. Okay, this one though is a little bit more defined. We know that it's increasing anywhere that it's going up from left to right. So from negative infinity all the way up to -1, we're increasing. And then we start decreasing here. We're decreasing because we're going downhill from -1 all the way down to 1. We're doing open circles because it's not actually increasing or decreasing at this point. And then we're increasing again from 1 to infinity. So we have our increasing and our decreasing, no constant parts where it's actually staying constant. Okay, finally, we have this function here. We see that we're increasing in the beginning. We're going up from left to right, from negative infinity to 0 for x. And then this is where we're actually constant, from 0 to 2. And then we are decreasing from 2 to infinity. All right, so now what we're doing is we're going to be talking about relative minimums and relative maximums. So relative minimum is where it actually, this point is smaller than the things on both sides. So it's saying x1 is smaller than x, but x is bigger, and x2. So on both sides, these are bigger than where we are here. Relative maximum, if it's like that maximum point, if it's that top of a little hill there. So it wants us to go ahead and graph a new function. So y equals, clear it out, 3x squared minus 4x minus 2. We go graph. And it's asking us to find the relative minimum. So we can actually do this on our graphing calculator. We can go second, calculate. We can come down here. There's minimum and maximum, both as choices. So if I go to minimum, it just says left bound, something to the left of that minimum. And we scroll over, something to the right of that minimum. And it will actually tell us what the value for our minimum is. So it's saying the minimum is 0.6666 1, 2, 3, 4, 5, 8, 4, 8, and y is going to be negative 3.3333. And so when we're looking at this, the actual like relative minimum value there would be that y value, but we could write it as a set of coordinate points. Okay, last question, word problem. Don't get scared. During a 24-hour period, the temperature Y in degrees Fahrenheit of a certain city can be approximated by the model Y equals 0.026 x cubed minus 1.03 x squared plus 10.2 x plus 34, such that x is between 0 and 24, where x represents the time of day, with x equals 0 corresponding to 6 a.m. Approximate the maximum temperature during this 24-hour period. And so this one, it gave us a lot of information there. But really what it's asking, all it's asking us to do is to just look for the maximum for this one. And so that's something that we can just use using our graphing utility, our graphing calculator. So we go 0.026 x cubed minus 1.03 x squared plus 10 point, I'm all up in the exponent, sorry guys. 0.026 x cubed minus 1.03 x squared plus 10.2 x plus 34. And then it also gave us a domain, so we want to change our window so that it will match that. We want to go from 0 to 24 for x. So once my graph loads, go to window. My x minimum I want to be 0, and my x maximum I want to be 24. I may need to zoom out because this graph might be really big. Where's my graph? There it is. So we want to change our window some more so that we can actually see. So our x minimum and our x maximum should be 0 to 24, but this gave us an idea that our y maximum, it has to be larger than 40. It already tells us that our intercept starts at 34. So let's make it like 60 and see what happens. See if we can fit it on there. Almost. So if we make it a little bit more, we should be able to approximate that maximum. So let's make it a little bit higher than 60. Let's go 80. And a lot of this is having to play with that to see if you can figure out what fits. Okay, so now it's really easy to be able to point out where is that maximum? Right there. So I go second, calculate maximum, find my left bound, go to the left of it, and then my right bound. And it will tell me what my maximum point is. So it says approximate the maximum temperature. So let's think about which was temperature, X or Y. It says the temperature Y in degrees Fahrenheit. So if we're looking for the maximum temperature, our temperature is going to be that maximum Y value. So 63.928097. We could round to the nearest third decimal place. 63.928 degrees Fahrenheit. That's our maximum temperature. Thanks, guys.